And so we want to maybe look at this now in the context of that this is something to do with like little t is time. So if little t was time, what could the function RT be telling us? So in these vector functions, we just said that little t is some scalar. Now, if you say, oftentimes you could let little t be a time variable. Okay, so time since our plane took off, or time since the end of class, or something like that. And then, or time since a particle started flying through space. So then what would RT be? Position, right? Like the location in space, or position. Okay? So now what I want you to do for each of these is I want you to express the function, something relative to R, and then, so you've got 5 to do, and then determine if that function that you've expressed is a real valued function or a vector function. So when we say a real valued function, by real value, are we talking about the independent variable or the dependent variable? If I say it's a real valued function, is that talking about the inputs or the outputs? Right, outputs, right? And that's the same with a vector function. When we say it's a vector function, that's the inputs or outputs. Independent or dependent variable? Vector function. Vectors are blank stares. All my life, blank stares. Vector function. Vector is referring to the output, the dependent variable, right? It's what the function gives. If it's a vector function, the function is giving vectors, right? So if it's a real valued function, the function is giving you a set of real values for whatever you're putting in. Okay, so for each of these 5, determine, so express it, something relative. So I didn't tell you exactly what RT was. I just told you it's called RT. So express it using RT, and then tell me if it's a real valued or scalar function. Okay, go. So you're working on this, and you're thinking, or you're talking to somebody. Okay, so how would I express the speed function? Speed function. How about Jose?
So the speed would be the magnitude of the derivative.
Okay, the magnitude of the derivative. Agree with that? Yep. So we would write. Sometimes you see double bars. Double bars and single bars around a vector mean the exact same thing. They mean the magnitude of the vector. So why write more than you have to? Is this what you mean? That's the speed. Is that a scalar function or a vector function? It gives you a number, just how fast, right? It just gives you a number of how fast. Velocity function. Justin, what's that? Yeah. What's that?
The same with speed.
It's the same as this?
Yeah.
The exact same thing? So velocity now includes direction with it. Not only does it have speed, but direction. So what would it be? Yeah. So it'd just be this. Vector function or scalar function? Vector function, right? At any time t, there's a speed and a direction. And that vector is the value of the function at time t. Are we good? Okay, direction of motion function. Megan, did you get the direction of motion function?
I think it would be a vector.
A vector, okay. So what vector would it be? If all we care about is the direction of motion, what vector would that be? That's okay. John?
Is it the unit tangent vector? So
Unit tangent vector. Is that right?
Yeah.
Yep, unit tangent vector just gives us direction. And what is that? Where does that come from?
over t over the magnitude.
So, yep. So you take the derivative and you unitize it. Okay? Direction of turning. Direction of turning. Harrison, did you get that? Uninormal. Which is what? It's the unitized derivative of t, right? How is t changing, right? We said how is t, how t is changing is change in direction, because t is only magnitude 1. So if you take the derivative of t, or how t is changing, and then unitize that, you'll get n. So it's t prime divided by the magnitude of t prime. All right, acceleration function. What would that be? Jonas. Second derivative. Scalar function or vector function? Was it? Vector function. Acceleration has magnitude and direction. So all your vectors that you get from the acceleration vector, all the things that you get from the acceleration function are vectors, because it's magnitude and direction. So remember that vector functions can be represented by curves by taking all of the vectors and putting them in standard position and sweeping out the curve as little t increases. Okay, so what am I showing with the blue vector? Direction of motion, is it the unit tangent, is it t? Why is it not the unit tangent? Changing magnitude, right? It's changing magnitude according to the magnitude of that vector is showing. Right, so the vector, the blue vector, is showing direction, but also showing how fast the point is moving with respect to time. So what is that?
Velocity.
This is velocity, right? So this is our r prime function, but now in the context of motion, it's velocity because it's showing us direction of motion and speed. Right? The magnitude of those vectors is our speed. Okay, next one. What's this? Direction of motion with constant magnitude, right? So therefore it is unit tangent, right? So it has the same direction as the velocity. So it's like what? So the vector function is made up of speed, its magnitude, and t, its direction, right? See that? So it's red, so I'll use red. So this is comprised of, velocity is comprised of speed and direction. Put those two together and you get the velocity function. Make sense? Okay. So here's another one. So here I'm going to show, I'm still showing our, you'll see it in there in the beginning. I'm still showing the blue velocity vector, but I'm showing another vector, gold vector. So I want you to make some observations. So talk amongst yourselves. Everyone's talking to somebody. Just observe this gold vector. See if we can't figure out what the heck the gold vector is. Go, talk. What is that gold vector? So maybe I'll just go from... One, two, and 5.
Does it change back? Yeah.
So watch what it does.
0, 0, then it's second derivative 16. So it's like acceleration vector would be also in the forward direction.
Okay, so let's just, so this is complicated, right? This is complicated. But just let's throw out some observations. So just, what observation did you make? Anyone have a observation about the gold vector?
Yeah.
Like, for this kind of thing, the gold vector is like this, or, yeah.
It seems to be orthogonal to both those points.
Okay, orthogonal to, so what about now? Is it orthogonal? Sometimes it's orthogonal, right? Sometimes it's orthogonal, yeah.
Magnitude's changing.
Magnitude's changing. Sometimes is it look like it's parallel to velocity? And sometimes is it orthogonal to velocity? And its magnitude is changing. Any other observations? Yeah.
It looks like it's pointing where the blue vector is going to end up next.
Pointing where the blue vector is going to end up
So
next.
see how it,
What about now?
on this half of the graph.
Yeah, sometimes, right? Sometimes. Any other observations? So what's missing here? So what have we not represented yet? Acceleration. Could it be the acceleration function? Why does it freak out, right? Why is it going like, doesn't seem to have any rhyme or reason to its direction or magnitude? So let's put that question on the table. So like, is this acceleration or not? Let's talk about acceleration. Okay, let's talk about acceleration here. If r is the position function, then so we all agree the second derivative is the acceleration. It's the rate of change of velocity, right? The rate of change of the first derivative or the second derivative is acceleration. So you're very familiar with acceleration, like if you're in a car. What does that mean? It means you're speeding up or slowing down. But there's another phenomenon to acceleration. Changing direction, right? So if you are turning, even if you're going at a constant speed and you're turning, you're accelerating, right? Which way are you accelerating? So say I'm going in a circle at a constant speed like this. Which way so if I'm going at a constant speed, then I'm not accelerating in the direction of motion. But the turning is causing acceleration. In what direction?
Towards the center.
Towards the center. So think about at the top. What's happening to your upward speed? Your upward speed is you're slowing down going up, right? And you're speeding up going down, right around the top, aren't you? So that's acceleration, right? Because you're on the, just in terms of your vertical component, you're slowing down, and then you start speeding up down. Well, that's acceleration in this direction, right? I don't know why I'm not writing on the screen. That's why my beautiful tab board. Okay? So turning, just turning itself causes acceleration. So there's two parts to it. There's the speeding up, slowing down, which we're more familiar with, but just turning itself is acceleration. So speeding up, slowing down is in the direction of t. And then the acceleration of turning will be in what direction? What's the direction of turning? N. So you have acceleration in the direction of n. So therefore, we can separate, so our second derivative, our acceleration, is going to be the sum of what? Acceleration in the direction of the unit tangent vector, which is, this is the speeding up, slowing down part of it, plus the acceleration due to turning, which is in the normal direction. But if we were to take the second derivative, we would just get three components, x, y, and z, right? We wouldn't have any idea. If we took the second derivative of some given position function, we'd have no idea. It would be all jumbled together. It would just be three component functions, right? We just have the x component, y component, z component. And there'd be no indication of acceleration due to speeding up, slowing down, and acceleration due to turning. But this is a much more convenient way to think about it, right? Because you're separating out the two aspects of acceleration. So how do we get that? How do we get just the tangential component and just the normal or turning component of acceleration? Okay? So we know we're going to take the derivative of r prime, which is r double prime, which is the derivative of r prime t dt, right? And what can I can write r prime t as what? The velocity times the unit tangent, right? Or the magnitude of r prime of t. So that's the same as that. So this right here is the magnitude of, now I'm just calling it velocity, that's speed function, right? Scalar function. Is it fair? Is it okay? And I'm going to take the derivative of that. So how am I going to take the derivative of this speed function times the unit tangent function? How do I take the derivative? What will I need? What's that? Is it the derivative of v times the derivative of t? No. Product rule, right? We're going to need the product rule. We need the product rule, right? So we're going to do the product rule. And what will we get when we do the product rule? We're going to have v prime times t plus v times t prime. So this is how we get started, taking this acceleration function and changing it around. So already we see, look, we've got the acceleration due to speeding up and slowing down. So now this is we're gonna change things around to get this to be acceleration due to turning. Okay, so recall a couple things. That the curvature is the magnitude of t prime over magnitude of r prime, and that the normal is defined as the unitized derivative of the tangent function. So that's things from our past. So we're going to use those to kind of change the form of this, okay? We're going to use those things to change the form of this. So I'm solving for t prime here. If I solve for the magnitude, or t prime, if I solve for t prime here, if I solve for t prime here, it's going to be n times magnitude of t. And then I can substitute in, I get the magnitude of t is going to be the magnitude of r times kappa. Is that what I did here? Let's see. T prime is that times that. Right, and then the magnitude of t prime is kappa times the magnitude of r prime. So I'm just combining these to solve for t prime in terms of kappa, r prime, and n. So therefore I'm going to plug that into t prime. And then we have it. So we get what? The derivative of the speed times the unit tangent. That's acceleration due to slowing down and speeding up. And then we have this, again, combining these equations, not to get into all the algebra, but when you plug this in for t prime, then you get this. Kappa times, these are the same, right? This is v of t. So you're going to get v of t squared times kappa times n. So here are the tangential and normal components of acceleration. Tangential should make perfect sense. It's just the derivative of the speed function, right? Speed, then the derivative will be how fast you're speeding up or slowing down. And then the an is going to be the velocity squared times kappa. So your acceleration due to turning has to do with how fast you're going and then how curved it is, right? So that makes sense. So your speed is going to come into that, but then the amount of how highly curved it is going to come into your acceleration due to turning. So then, if this is the speed, no, that's unit tangent, right? This is the unit tangent. So is this going to be a matter of the acceleration in the tangential direction? Is it going to be dot product or cross product? Meaning we want how much of the acceleration is in the direction of t or orthogonal to t? In the direction. So then is that going to be dot product or cross product? That should be dot product, right? Maybe? Not in this mode. Yep, so it's going to be dot product because we want how much of the second derivative is in the direction of t. So that should be dot product, right? That's what we said about our definition of dot product. And then, again, we can kind of see kind of see t in there. So now, if it's the direction due to, or the acceleration due to turning, do we want how much of that that's in the direction of t or orthogonal to t? Orthogonal now, right? So now we're extracting the part of the second derivative that is orthogonal to t, or in the direction of n. So, dot product or cross product? Cross product. So those formulas should make sense. So when we're actually calculating AT and AN, so AT is kind of maybe either way. This might be doable, but that is convenient too. For AN, you're probably going to want this one. Because that curvature formula can be pretty messy. So these are kind of the formulas that you might use to calculate, and they should make sense because of how the dot product and cross product fit in there. Okay, questions on the derivation of acceleration? So the big takeaway here is the second derivative of a position function is the acceleration, and that is broken into two components: acceleration due to speeding up and slowing down, that's the tangential acceleration, and acceleration due to turning. Right? That's the acceleration in the direction of the unit normal vector. So let's go back. And so if we were to do r double prime on this, what would we get? Negative sine, and the derivative of that would be negative cosine, and then the second derivative of this polynomial, and then the second derivative of that. Would that give us any indication of tangential acceleration or normal acceleration? Let's do it fast. So r double prime. Here we go. Where am I? Negative cosine is the second derivative of cosine. What's this? 4t cubed, 12t squared. 12t squared, 24t. Trying to do two derivatives at once. 66. Did I do it right? And it's going to be negative sine 5t, but then times 2.5s. Did I do the second derivative right on all those? All right, so what's the acceleration due to speeding up and slowing down, and what's the acceleration due to turning? Don't know, right? It's all mixed together in there. It's all intertwined. So with those formulas that I just showed you, you can separate it out. You can do what? I don't know what it is. R prime t dot r double prime t over the magnitude of r prime. Is that right? If you work that out, that would give you a scalar function, right? A dot product divided by a scalar function. That would give you a scalar function, which gives you the acceleration due to speeding up and slowing down only. You multiply that by the unit tangent, then you get the acceleration speeding up, slowing down vector. Same thing with the formula for the acceleration due to turning. Does that make sense? Following this? So just taking the second derivative, it leaves them all intertwined. You can't see the difference. But then those formulas that we derived can give you each separately and let you write that acceleration as the sum of the two different components. Okay, so let's look at the picture again and see, is it acceleration? Does it seem to be the acceleration, and why? Yeah.
Because when it's turning, it's orthogonal, and when it's going straight, it's in the direction of.
Okay. So right now it's turning, but also, how is it turning? Is this consistent with the goal being acceleration? Yeah, go ahead.
Oh, yeah, because as the graph goes on, the vector shrinks, so you know that the acceleration is like decreasing magnitude of the velocity vector.
So right here you're saying right here at this time, the velocity vector is decreasing.
Yeah.
Okay, and therefore the acceleration is
So the acceleration is
right. It's slowing down, right? So here right now we're slowing down, and how much turning is there?
not much.
It's like going straight, right? So it's going straight and slowing down. So what do you expect for the acceleration vector? Opposite direction of motion, right? There's no acceleration due to turning, and we're slowing down, so that is consistent, right? What about here? What's happening here? How about this? How about the speed? What's the speed doing? Look at the blue vector. What's the speed doing? Through the loop. It's staying pretty constant, right? So then what about acceleration due to speeding up and slowing down? 0, right? Therefore, all the acceleration is in what direction? Unit normal, because it's all due to turning, right? All the acceleration is due to turning. So that acceleration is mostly in the direction of n at this point. Okay, what about something like this? How can we explain what's going on, say, right now? Is there turning? Yeah, because it's not, there's a little bit of turning. Is it speeding up or slowing down? Speeding up, because we've got a, if you look at that vector, it's got a component in the direction of t, but it also has a component in the direction of n. It's both. So you have some acceleration due to turning up, and you have some acceleration due to speeding up. So then the combined, you add those two together and you get this vector. How about now? What can you say about the motion right now? No turning. Speeding up or slowing down?
Speeding up.
Speeding up. Make sense? How about now? Speeding up or slowing down? Constant speed, right? Constant speed. And? But we're turning which way? Turning down, right? Turning down. So all your acceleration is due to turning, pretty much orthogonal to in the direction of n. But here the speed is pretty much staying constant. I love this function. It's awesome. Okay, any questions? Does it make sense? Last chance. Pretty cool. Okay, so let's go on and talk about new subject. Multivariable functions. Multivariable functions. So most of the functions we've encountered in your math career have been y equals a function of x. So is this a scalar function or a vector function? And by scalar, am I referring to x or to y? Y, right? Scalar function means that what comes out of that function is just real numbers, okay? And so is this a single variable function or a multivariable function? And that's referring to x or y? X. So a single variable function means how many variables create the input scenario. And then if I say if it's a scalar or a real valued function, that's talking about a real value comes out. So this is a single variable, one independent variable, real valued, one real value dependent variable function. Single variable, real valued. Single variable, real value. That's the land you've lived in for a decade, okay? All right, let's talk about this one. So, single variable or multivariable, real valued or vector valued? Single variable, vector valued, right? Single variable, vector valued. So what's a multivariable, real valued function? That's what we're going to talk about in this part of the course. A multivariable, real valued function, what would that be? Yeah?
You have two independent variables of x1, x2.
Okay.
Output is a scalar quantity.
So you said you have two independent variables that are your input, and then based on those two, it'll spit out a single value, a real value. That's it. Yeah. So how might we represent that? If the function is function f, then what might that look like? So it's going to be z equals a function of x and y. So now y and x are both independent variables, and given ordered pairs, your function spits out a real value for every ordered pair. So how would those graph? I don't know if that's the next question. All right, so here's one. Wave height is a function of both wind speed and duration of time. I wish I would have taken a video. It was in Rocky Point last year. And the wind was blowing so hard all day long. And by like late afternoon, the waves were so high that I almost couldn't go in the ocean. I was scared to go in the ocean because I was going to crack my neck getting turned by these waves. But they were like 10 feet high. They were ginormous, okay? And so that was because the speed was blowing at such a high rate for such a long time that resulted in high wave height. Okay? But a real low velocity wind for a long time isn't going to result in much wave height. And really high gusts of wind just for a couple minutes are not going to result in much wave height, right? So it's a function of both. The wave height is how long the certain winds are blowing. Gives a certain wave height. Okay, so we have different representations. I think there's 4 that we want to talk about. 4 ways to represent these functions. The first is a formula. So we saw z equals x squared plus y squared. What is that? What is z equals x squared plus y squared? Oh, we gotta know this. Yes, sir. Yeah, this was the circular paraboloid, right? Our basic one. So now we can rewrite this, rather than saying z equals x squared plus y squared, we could say f of x of y equals x squared plus y squared, and make it into a function. So this is the first representation, a formula, or i.e. a function definition. Okay, we can graph these in R3. How is this going to work? If f of xy equals x squared plus y squared, then how is this going to work? So what is our input then? Or where is our input? Where does it show up? Now our input is an ordered pair of x and y. Where's that? Yeah, so rather than just our x-axis being like the launching point, now our whole plane, the whole xy plane, represents values of the independent, right? Pairs taken in combination. And then for every given xy ordered pair, the formula tells you the corresponding z, which is height, right? Be negative, doesn't have to be positive. So given an xy ordered pair taken together, which is some point in the horizontal plane, there's a corresponding z, which we graph as height. So what kind of thing will we get when we graph a multivariable real valued function? What kind of graph representation will we get? We'll get surfaces, right? We know that that paraboloid is a surface. We're going to get surfaces. So this particular surface is circular paraboloid. So for every xy, you get a corresponding z. When x and y are 1, you get z equals 2. When x is 1 and y equals 3, you get z equals 10. So a surface. A surface in R3 is another representation of these multivariable real valued functions. Next one is traces. So where z equals k. Remember we said these were level curves. So when you do traces, where you let z be constant, different constant values, and then you graph what you get in the xy plane. If you do that many times, you get what's called a contour map. So for x squared plus y squared, so if z equals 1, what do I get? If z equals 1, what do I get in the xy plane? Circle, radius 1. When z equals 2, what do I get? Try again. Circle, not radius 2, square root of 2, right? It's going to be circle radius. So when z equals 4, then what do I get? That's with circle radius 2. So this is z equals 4. This is z equals 1. So it's also kind of like a topological map, right? So staying on a curve means staying at a constant z value. Moving from curve to curve means changing z value. But you put these all together, so for a paraboloid, it's going to be all these concentric circles. And if I kept my z's constant, if I did z equals 1, 2, 3, 4, okay, how will the circles be spaced? Evenly? Okay, will they get closer together or further apart as I move away from the origin? Further apart. All right? So for constant z values, those circles will get further apart. Is that right? Oh, now they're saying closer together. What about you guys in the back? What do you think? What happens to the rate of change as we go higher in z or further away from the origin? So for the same change in z, am I seeing smaller changes in x and y or bigger changes in x and y? Smaller changes in x and y, because this thing is getting steeper, right? So for the same change in z, so will the circles get closer together or further apart? Closer together. Does that make sense? For the same change in z, you see less and less of a movement outward because this thing is slanting up. So this contour map will be concentric circles that get closer together as you move away from the origin. That's traces. Yeah. Okay, another representation of these functions is a table of values. So let's create one for the function f above. Now you have a two-dimensional table rather than your standard one-dimensional table. So you could say like x and y does. So you could let x be -1, 0, 1, 2, 3, y, 0, 1, 2. And now given values of x and y taken together, the function tells you corresponding values of z. So when x is -1 and y is 0, z equals 1, according to the formula, right? And when x is 0 and y is 0? When x is 1 and y is 0? 4. Now y is 1. X is 1 would give 2. X is 0, y is 1. Okay. Both are 1. X is 2, y is 1. 5, right? Y is 2, x is -1. 5, 4, 5, and both are 2, etc. So these are all different ways that we can represent a multivariable single-valued function. With a formula, with a surface in R3, with a contour map in R2, xy plane, level curves, and with a table of values. So just one example here. So I want you to sketch that function. So I'm giving you the contour map, and I'm asking you to sketch the surface. Given the contour map, can you sketch that surface? What will that be like? Quick, you got 1 minute. So here I'm showing you the z values. So here about 0.9, you have a z value, constant z value of 0.4. And here on the x-axis, there's a contour line with a z value of 1. So I think these are all 0.2. So what would this surface look like? And maybe can we figure out from that surface then what the function formula is? Yeah?
Is it like parent
The plane, so it's,
Yeah, slanted.
what's that?
Slanted like downwards when slanted upwards from negative I values to higher I values.
So are you saying that it's a plane? Planes are flat. Is that what you're saying?
Yeah.
Is it a plane?
Is it like a cylinder of like z equals dx?
Okay, so a cylinder of an exponential function. So what happens here? As we go in the what? The negative y direction, what happens to the surface?
It increases in the same value.
It's going to increase. And then as we go in the positive y direction, it kind of flattens out, right? Because these are far apart. And where they're close together, it's going to be steeper. And then this tells us if you move in the x direction, you're going to stay at constant z. So what kind of surface is that? Cylinder, right? So this is, yeah, so this is an exponential, you got it, it's an exponential cylinder. Let's see. Where's it? Come on. Oh, that's because that's the video. Where is it? There we go. There's the actual thing. Is that what you were imagining? If you were imagining that, then you were reading this correctly. Okay? So this is z equals negative e to the negative y. An exponential cylinder in the x direction.